All right, so lecture 3 covering chapter 4. And this is where we get into Newton's second law. And the intro here is just talking about some history of Newton. But we'll check out what comes next. So, force. What happened? So, Newton, through some math stuff, came up with F equals ma. But this was actually known at Newton's time from experiment that if they would collect their data, have this axis as the acceleration of an object, and this is the force applied. And they get some data. I'm just kind of imagining what it looked like, and then you could see it had a linear relationship to it, which supported this result. And so the force you apply on an object will equal the mass of that object times the acceleration it will then have. And then mass here is inertial mass. Mass is a measure of how resistant you are to motion. So if you apply the same force, something that's not massive, well, let's say you apply 10 newtons of force, and if something has 2 kilograms of mass, then that would be an acceleration of 5 meters per second squared then. But if you apply that same amount of force and say something is a lot heavier, maybe 10 kilograms, well, then we see the acceleration is only 1. So mass is a measure of your resistance to motion. The same force being applied, 10 newtons, but the more massive you are, the less acceleration you'll experience from that. And as we're talking here with forces, that in order to get something to move, you have to apply a force. You have to apply a force to give that object an acceleration so it can start moving. And friction. So I see they got a picture here. Maybe I can exaggerate that a little more. But on the atomic level, so all of this seems really smooth, but if we look at the atomic level, it's very jagged because it's not formed perfectly. And when you have two objects that are touching each other, you get this really jagged interface. And so things get locked together. And we call this initial force that you have to overcome static friction. It's the friction that you experience when something is just stuck to the ground. It's kind of interlocked with the ground, these little cliffs and valleys on the atomic level. They're just stuck there. And that's the picture they're trying to show over here, this jaggedness and how things get stuck. And when you push something, you have to first overcome this. So you got to kind of lift all these valleys out and start bumping it along. And that initial force takes more force to get something moving. And then once you have it moving, things just kind of bump along then as they move along there. So initially, kind of things are stuck. You got to push hard to get that thing moving. But once it's moving, a little easier to push because once things are bumping along, they're not stuck and interlocked together. And that's probably what they're saying here with this picture. Trying to move something, that first push, pretty hard to get it going, but once you can get it going, it's usually a little easier to keep it going. And so once it is moving, we actually call this kinetic friction. Kinetic meaning when something is in motion, but they are calling this sliding, so I'll stick with that, sliding friction. I guess I can't use S again because that's at static again, but we do call that kinetic. Kinetic meaning something that's in motion, where static means it's not in motion here. And the static force, when things are interlocked together, sorry, I'm interlocking my fingers there, I guess, that's always greater than the sliding friction. And they got some, just looking at these check answers here, I see they're getting 0. And what they're saying there is, well, let me do this. Let's say you got a block and you're going to push on it with 20 newtons of force. And as you push on it, let's say the static, that initial force of friction, let's say that's 10 newtons. It's initial force of friction always working against your motion. So if you push with 20 and static is 10, well, that means you'll be able to push it because your force is greater than the static friction. But if you pushed, say, with only 5 newtons of force, but static is working back at 10, well, then you won't be able to move it because you're not pushing hard enough to get all the interlockings here to start sliding. So it'd still be stuck there. And I'm sure it's happened, you know. You push on something like a car, and it's going to take a lot of force to overcome static friction with, you know, heavier things. But once you get it going, so say this situation up here, so here you'd have to push harder, it's stuck, but here you've pushed hard enough to get it moving. If we take this picture again, this first one, since it's moving then, and so say you're still pushing it, well, now we would have kinetic friction, this what they're calling sliding friction. And if you're going to push with constant velocity, so, you know, just like when you drive the speed limit, if you're going to push with constant velocity, then the friction working against you would have to be the same as what you're pushing at. And that's what they're showing over here. When they sum the forces, they're saying when we sum these forces, we have this force applied that you're pushing on going to the right. To the left is this kinetic friction working against you. And if you're going at constant velocity, then that means that equals 0. And this is always a thing with a tire, that getting a fatter tire doesn't increase the friction. Friction is actually dependent upon the normal force of the car, the weight of the car if it's on a flat surface. So no matter how fat your tire is, the weight of your car is still pretty much the same. But having a fatter tire increases the traction, because you always want to have traction with the surface, and fatter tires can definitely help with that. And that is friction. There's a little bit more of the friction. Friction is always when you have surface contact. So, you know, if I just draw a table and you put sun on the table, whenever you have surface contact, that's when you have friction, what's commonly called friction. Because I want to differentiate this from if you have an object in the air. And so you say you just drop some object and it's fallen down. Well, I know they're going to say in a little bit, they're going to talk about air resistance. And this is in the atmosphere. As your object falls, it's hitting all these particles as it falls. And then we get this air resistance. And we tend to call objects in contact, call that friction when two objects are in contact. But things falling through the air tend to call air resistance, even though, you know, technically you could say it's friction, but tends to be differentiated. Friction surface contact, air resistance in the air. Mass and weight. So the gravitational field from the Earth, because the Earth is so large, and we're just tiny on that. And the Earth's gravitational field does change, but at this radius, and because we're so tiny, the Earth's gravitational field seems constant to us in our little area here. And we call that G, 9.8. Or for us, it's 10 meters per second squared. And that force you feel from the gravitational field, so Newton's second law is that force equals your mass times acceleration. Well, if this acceleration is due to gravity, then this is the force from gravity. And this is also very commonly called weight. So the weight you feel when you're walking around, that weight is the force from gravity. So commonly use these two words. I might say technically it's better to say force from gravity, but weight is what we normally say in just walking around in everyday life. You know, I guess if you walk up to somebody, you probably don't say, "Hey, what's your force of gravity?" You probably don't go up to people and say, "What's their weight?" either, but same idea. And I just noticed they're showing a scale. When you step on a scale, I guess that's a giant scale, your force of gravity, your weight, is going down. But whenever you have surface contact, there's always what we call the normal force, or the supporting force, going up. And the scale actually reads the normal force. That's what they're calling a support force over here. And if you'd stand on a scale in an elevator and it moves up, well, then the scale isn't going to read your weight anymore, because if you're accelerating up, you're going to feel heavier. And the scale will read something heavier than you actually are. So I think their point they're trying to make here is that the scale only gives your correct weight when it's on a flat surface and there's no acceleration. I just noticed a person floating around with an anvil. So weight is the force of gravity. So if you go to, say, the moon, if we got Earth and here's the moon, well, the moon has a smaller gravitational field. Gravitational field is created by how massive something is. Since the Earth is much more massive, stronger gravitational field, and we measure this to be G, but let me call that Earth. On the moon, this is much less. The value for gravity on the moon is much less. So if you would go onto the moon, your mass stays the same. Your mass doesn't change from Earth to the moon. Still the same mass. What changes is your weight. And the reason your weight changes is because the acceleration due to gravity changes. So your weight over here, m times gravity due to the Earth, which is 10, and then your, let's say, Earth, weight on Earth, and then your weight on the moon is your same mass, but then the acceleration due to the moon. I think it's a sixth. That's what they're talking about there. Is that pushing an elephant on wheels? And talking about how mass resists acceleration. I tend to say it resists your motion. I think it's a little easier to get around the idea that what is mass? It's a quantity. The higher your mass, the harder it is to change your motion. Mass is your resistance to being moved. So Newton's second law. Newton's second law is stated as F equals ma. And with math, you can divide both sides by m and get F over m equals acceleration. And that's what they're showing first. But this is Newton's second law, F equals ma. And then using math, you can rearrange it to get to that. Well, this is just some math stuff. Thumbs up and up down. I guess they're talking about the numerator or denominator. Something that's directly proportional just means something that's linear. And in this case, F equals ma is something directly proportional. I guess that's why thumbs are up, because both of these are in the numerator, all this stuff. Inversely proportional actually has a graph that looks like that. And it just means that you got something in the denominator. Like if I divide both sides by m, whoops, it should be an equal sign there. But now we have something in the denominator, then it's inversely proportional. Not quite sure why that's just math stuff. And here they're saying that what I was talking about before, that if you apply the same force, so when they say the same force, that as the object gets heavier, then the acceleration is lighter. So this is a quick example for the first one. Let's say you push the brick, a mass of one brick there, and it has some acceleration. But now if there's two bricks, same force, but now if you have two bricks, well, that means you have two of these bricks that both weigh mass m, and you'll get a different acceleration. You'll get half the acceleration because it's the same force. So for instance, if we push with 10 newtons of force on this brick, and let's say the brick weighs 1 kilogram, well, then your acceleration would be 10 meters per second squared. But if you have two bricks, now you got two bricks, and so now you're dividing by 2, your acceleration is halved. And same if there was three bricks, 4 bricks, and so on. We could solve for a then. In his case, we're starting to get fractions though. Oh, I guess they do have a third here. Oh, looks like they're going into free fall. So, free fall is technically defined when your acceleration is only due to Earth's gravitational field, g, versus when they talk about air resistance. So air resistance is not considered free fall because air resistance will slow your acceleration, and your acceleration will no longer be just due to the Earth's gravitational field. So that's what they're starting out with here. When the acceleration is only g, we call that free fall. Um, well, here's another math thing. I don't know if you know this, where pi comes from, but the circumference of a circle, the length around it, diameter is when you pass through the center, go from side to side, that's the diameter. And they figured out thousands of years ago, no matter the size of the circle, whenever you do circumference divided by diameter, you always got the same number. And we call that number today pi. But just a result, thousands of years ago, they recognized this with circles. That's how you get this constant number for all circles. I get pi. But that's just a math thing. We're leading into air resistance. So let me say this, because I see they're doing this red circle with the rock and a green circle, which is smaller, with the feather. And when we go into air resistance, which is what's coming up next, let me use this picture here, though. That air resistance depends upon the area that's being presented to the air. So I'm going to try to do this kind of three-dimensionally, but if stuff is coming at you, then the air resistance is dependent upon this area of contact here. And this could be some strange object, I don't know. But when things move through the air, the resistance is just what hits it at the surface. And so they're approximating this basically with circles. And when a sphere falls, then what's in contact with the air resistance here is just this circle. So, the air resistance doesn't go around and hit the sphere in the top here. The air resistance is just hitting the initial part in contact here, and anything above the equator line there, isn't being hit anymore. And that presents a circle to the kind of this area here. And when you have a smaller object, then there's less surface presented to the air resistance, and so there's less air resistance. With skydivers, if you want to go really fast, if you jump out of your plane and you want to go fast, well, then you do the kind of Superman thing, point yourself straight down towards the ground. And why would you do this? Because then the air resistance is mostly just coming from your head and your shoulders a little bit. I'm drawing a stick person here, but your shoulders are wider than your head. But that's what would hit you, the air resistance there. Where as if you would, kind of fall like you're laying down. Well, now you're presenting more of your body to the air resistance, and then that causes you to fall slower. Another idea with this is actually with parachutes. What the parachute does is it gives a larger area. It's a much larger area that the air resistance hits. And that larger area gives more force up then from the air resistance. And here it is. So when acceleration is less than g, they're going to talk about air resistance. And they're just going to give some numbers here. So showing a person falling down. They haven't opened their parachute yet there. But the wingsuit, the reason this is helpful is because you're increasing the surface area. So instead of your body just being like this, now you have this extra surface area from the wingsuit, so that's more air resistance that you come in contact with, which increases the friction from the air resistance, and that slows you down. And here's some parachutes. Um, so I'm gonna take a guess here. If not, it's still something I'm sure they want said here. They're they're using M for both of these people, which mathematically means they have the same mass. But this green dude looking a little chunkier than the blue person here. So I'm guessing it's these are meant to be different masses. So um, I guess I'll draw the bigger person like that, and then my good old stick figure. These technically have different masses. I mean, I'll just call that mass large, mass small. They technically have different masses, but um, they roughly have they roughly have the same air resistance. So just because the green guy here is a little bit chunkier, they're still presenting about the same amount of air resistance as air resistance hitting them. There's going to be a little bit more, but not too significant. And so what they're going to say here is that they're basically facing the same air resistance, that they have the same air resistance. If not, they're very similar. But they weigh differently. So remember, weight is dependent upon mass. And so this person weighs more because they weigh larger. Their mass is larger. And so when we take our weight is going down for this person. And then they have their force of air resistance up. This person over here is going to have less weight going down, less because they have less mass, but the force of air resistance is still going to be about the same. And so the heavier person will fall faster, is what they're showing here. If they both experience the same air resistance, then the heavier person has more weight. And so that's pulling them down more than air resistance can pull back on. And they're showing that with what is that? Ping pong and a golf ball. So, wow, this is actually a really good example, actually, because the ping pong and the golf ball are about the same size. So, ping pong, and I guess the golf ball's got dimples in it. So there's my dimples. They're basically the same size, and so they have the same air resistance. So I'm using force R, force for resistance. Oop, be that R there. So because they have the same area that's being presented to the air as they fall, this bottom part here, they experience the same air resistance, but this one weighs heavier. This is a heavier weight. This one weighs lighter. And so there's more force on this one because it weighs heavier, and this one not as much. So if they're about the same size, then the more massive object will fall faster when we have air resistance. And this is something, this is always the common case with the feather. If you take a feather and a pen, they're about the same size or something close, but the pen's a lot heavier and it'll fall faster. They're using R here. I mean, nothing wrong with that. Just looking at what they're writing here. So they're just summing these up by saying net force that if we look at the net force on our object, that we got the force of air resistance going up. They're just calling that R. I like to use F sub R, but they're just using R. That's the force of air resistance going up. We have our weight coming down. And then Newton's second law says when you add up all these forces, this equals ma. That's Newton's second law. And then in the book over here, all they're doing is dividing by m. If you divide both sides by m, you get A equals that result. Oh, and they're also, just looking at it again, weight. Remember, weight is the force of gravity, which is mg. And they're plugging that in. So weight is mg, and then divided by m to get A there. So that's what they're showing on the right here. And let's check out some homework. All right, so looking at the practice, number 1, how does acceleration depend on the net force? Well, F equals ma. That's Newton's second law. He does have a first law and a third law, but just focusing on the second. Again, we say this is proportional. That's the math language there. And that's the third one. Acceleration is proportional to the net force. Proportional, again, just means when you get something that's linear when you graph it. So XY coordinates, Cartesian coordinate system. When a crate is pushed horizontally and doesn't slide, all right, so I got a crate, pushing it horizontally, and it doesn't slide. So that means my applied force and the frictional force, if it's not moving, then we're in a static case. So that's where everything's locked together here at the atomic level. So when we sum of our forces, pushing to the right with our applied, friction working against us, it points to the left, so it gets the minus sign. And if we're not moving, then, well, Newton says summing our forces equals ma. But because it's not moving, acceleration is 0. So, whatever your mass is times 0 gets you 0. And that means the force of friction must equal the force that you're applying. And so where is that? The friction force is equal to the mass of the crate. Well, no, it's not moving, so no acceleration. The friction is 0. No, it wouldn't be 0 because then the crate would be moving. The friction is equal to and in the same direction. Well, it's not in the same direction. It's opposite your direction. Friction always opposes motion. And the frictional force is equal and opposite. So there's what we're looking for. It's equal and it's opposite. And what is this? What is the weight of a 1 kilogram brick? So, again, F equals ma. Newton's second law. When we're dealing with the force of gravity, then acceleration is g due to the force of gravity, and this is commonly called weight. Weight, just to say it again. Because, some people get them mixed up or get them separated. Weight is the force of gravity. They're the same thing, just different names for the same thing. And if they're saying our mass is 1 and g is 10, so that's 10 newtons of force. if the mass of a sliding block is doubled, so we got our block, it's sliding, so it says, well, I'm just, pushing it again, with some force, some applied force, friction working against us. If it's sliding, then we're in the sliding friction. Again, commonly called kinetic, meaning when something's in motion. So now it's moving because they're telling us that it's sliding. So it's moving. The mass is doubled while the force is the same. Well, the force is the same. How much does the acceleration change? Well, if we have our summoning our forces, just add them all up. Our force applied to the right, friction working against us. When we sum these forces, this is Newton's second law, that equals mass times acceleration. And if we double the mass, so this stays the same. Remember, this stays the same. We're pushing with the same force. We have the same force of friction. So this number stays the same. And we're changing then just the mass. So if we go to half of the mass, well, for this to equal the same thing means we'd have to have twice the acceleration. Now, I notice I just said this. I halved the mass, though. The problem, so that's what happens if you half the mass. If you half the mass, then you're going to get twice the acceleration, because 2 times a half, those will cancel out. You'll go back to MA. Remember, this stays the same. That's the crucial part, that your applied force stays the same, your frictional force stays the same. So when you subtract these, this is the same number. It always stays the same. If we double the mass, we double it, well, for this to equal the same number means we'd have to have half the acceleration then. And I just put that in parentheses. So that's what they're saying here. If we double the mass, that will half the acceleration. And where does it say that? The second one. I was just looking at the first one. That says a quarter. We got quadrupled. It's the same. Acceleration is doubled. The acceleration is doubled right here. If you half the mass, that's when the acceleration will be doubled. So which of the following statements is true about a falling object that has reached terminal velocity? Oh, I guess I missed that in the book. So air resistance, I'm just thinking about it because air resistance is actually pretty complicated mathematically. Not only does it depend upon, let me just use a sphere again. Not only does it depend upon how much contact you have with the air, but it also depends upon how fast, what your velocity is that this thing is falling at. So if you would jump out of the plane here, so I'm just drawing your center of mass. Imagine you're just this point. When you first jump out of the plane, you experience the force of gravity, which is your weight. And then as you fall, so your weight stays the same, but as you start moving, the force from air resistance starts to increase. Now how much air you're exposing to the air, just imagine we're keeping that constant. You're just falling down. So you're keeping that constant. But what's changing is your speed. As you fall down, you accelerate, you're getting faster and faster. And air resistance is also dependent upon how fast something is moving. So as you go faster and faster, the air resistance increases until you get to a point where it exactly equals the force of gravity, where it exactly equals your weight. So that when you sum the forces, we'd have air resistance up, we'd have force of gravity down, and now that they balance, this equals 0. And this is what's called then terminal velocity. This is the velocity at which the air resistance equals your weight. And you have to achieve that by falling faster and faster. And again, air resistance is mathematically pretty technical. It does deal with the area exposed. So if you change the area exposed, if you make it larger area exposed, that increases the air resistance. And what also increases the air resistance is how fast you're going. The faster you go, that also increases air resistance. Those two things. So let's just see which of the following statements is true about a falling object that has reached terminal velocity. Well, at terminal velocity, the sum of forces equals 0. That's what terminal velocity means. That's the fastest you can get. Can't fall any faster from Earth's gravitational field. And air resistance, and this last one here, air resistance and weight are equal. So they're equal because they cancel each other out, and they're in opposite directions. If two objects of the same size move through the air at different speeds, so they're the same size, and let's just use spheres, so the air resistance is both hitting these same size of circles as it falls down, but they have different speeds. So let's say this one is going slower, and let's say this one is going much faster. Then this one here has more air resistance. And that's because its speed is larger. And the faster object, here we go, the faster object encounters more air resistance. I just feel compelled to say this. I mean, this isn't in the homework or anything, but, like the force of gravity, which we commonly call weight, is equal to mass times gravity. The force of air resistance is equal to this number that's proportional to many things. Part of this is your surface area. Part of what goes into the sigma value also has to deal with what the air is like, how many molecules are hitting and stuff. And it's times v, which is the velocity then. So as your velocity increases, so does your air resistance. But this isn't in the homework or anything. I just thought I'd throw that out real fast, that what it means to be proportional. Here's where the area part is. It's inside there in that number. And then here is the velocity part. And you multiply those two together. What is the net force acting on a 2 kilogram ball in free fall? So free fall means the acceleration is only due to gravity. And using that Newton's second law, the sum of forces equals ma. Well, if acceleration is g, then we can just throw that in there. And they're telling us the mass is 2. And then times 10 for gravity to get us 20. And, let me get my keyboard back. A couple more values here. So what's this last one? We got Alex, who has a mass of 120 kilograms. So Alex, a pretty big person. Average mass of an adult is 70 kilograms. So Alex is a big person. He's skateboarding at that speed. So he's got a speed 7. Oops, I put mass here. That's just the average mass of a person. Alex is 120, and they're telling us the velocity is 7 meters per second. When he smacks into a brick wall and comes to a dead stop in 0.2 seconds. All right, so we get a time here, 0.2 seconds. This reminds me there was another part in the book here. This is another reason why I'm glad to go through these problems in case I missed something. But acceleration is the change in velocity over change in time. So let's say you start at a stoplight. Your initial velocity is 0, and then you go to the speed limit. Let's say a final velocity of 30 meters per second. That's about 60 miles per hour. Well, that change is always final minus initial. So if we do 20 minus 0, that change is 20. Your velocity changed by 20. And let's say that took you 10 seconds. Well, 10 seconds is your change in time. And so we can get your acceleration from that. That would be 2 meters per second squared there. So if we look at the information they gave us, we got Alex on his skateboard cruising with the initial velocity of 7, but then he hits the wall and then his velocity is 0. And it took 0.2 seconds. So the change in velocity was 7, and that occurred in 0.2 seconds. And they do want a number here. So I get my calculator. And that is 35. Now we'll see what happens here with the book, but let me just say this. These deltas, these math symbols, are always defined as final minus initial. Now in physics, we almost always take time initial to be 0. So the bottom here is just time final, which they told us is 0.2 seconds. Our final velocity, because we stopped, the final velocity when he hit the wall is 0. And then we have minus the initial, which was 7. So this 35 we got is technically negative. So negative acceleration, that's what happens when you hit your brake, when you need to slow down, also called deceleration commonly. But we'll see. Let's see if they want the minus sign. Well, I can see that they don't. And they're using another a math word here. So they say, what is the magnitude? Magnitude means the absolute value. So, if A is minus 2, well, the absolute value means just get rid of the minus sign. So for us, A was, what was it again? Minus, so for us, A is minus 35. They're asking for the absolute value, the magnitude. So they are telling us to just drop the minus sign there. And that's because of the word magnitude there. And then what is the force? So force, Newton's second law, ma. Alex's mass was 120. We just figured out the acceleration is 35. So let me get my calculator out. It's be 4,200. And there is the last homework problem. And I will talk to you in the next video.